70% of construction rework comes directly from design issues. That equates to around 5 to 10% of the average project's costs. And that's before you factor in schedule delays, indirect costs, and angry clients. In the past, contracts were simpler. You get a set of drawings and you build what's on the drawings. Now, projects have multiple technical interfaces, complex design requirements, and complex stakeholder approval processes. Even traditional construct-only contracts typically have quite significant design obligations when you factor in subcontractor and procurement design scope. RFIs pile up and design approvals tend to take more time than the actual construction works. The reality is, to effectively manage a construction project, you need to be able to effectively manage the design. So in this course, we're going to be covering the fundamentals of design management on construction projects. We'll talk about why it matters, what it is, how to read and understand engineering drawings, an essential skill for anybody in the construction industry, and the stages of design management, the development stage, and the construction and closeout phase services. So let's start off with the all-important question of why does design management matter? While the typical design costs on a construction project typically represent 5 to 10% of the overall project budget, the design scope impacts 100% of the construction costs, the time outcomes, and the quality outcomes. Get the design right, the project will be easy. Get the design wrong, and you'll die a death of 1,000 cuts. Let's make this a bit clearer. What happens on a project if you ignore design management? You sign a contract without understanding what your design obligations are. Your consultants design in isolation. They don't pay attention to how much it's going to cost to build or how long it's going to take or whether it's even feasible. The client doesn't sign off the design, which delays your construction start date. The design is over-engineered, you clash with services, or it can't be built without a ton of RFIs and rework, delaying construction, and you miss key stakeholder requirements like development approval conditions or utility requirements that end up delaying the project handover. You then start on site and you start trying to build this incomplete design. Your team is building off incorrect drawings and revisions. RFIs pile up, delaying every single construction activity. Subcontractors issue variations because they've priced off the incorrect revision of the design or even wrong design. You redesign on the fly. Quality suffers and the client loses faith in your ability to deliver more projects, preventing you from getting further work. Doesn't necessarily sound like the best project to work on. Well, design management is the solution to all of these problems. It aligns what you're agreeing to build with what your budget is. It ensures that everything's ready to go when you need to start works to meet your program. Coordinates between disciplines and resolves issues early. It manages design changes through proper change control systems, and it also ensures you cover yourself for any variations or client changes, and documents what we've built so it's easier to close out and hand over the project and get paid on time and finish the job. Ultimately, design management protects your profit margins. Every uncoordinated drawing or design change can become a variation to you from your subcontractors or a variation from you to your client. Every design delay costs you time and money you don't have, and every scope gap or over-design eats into your profit margin. You're building something that you originally didn't budget for. Ultimately, the design is telling us what we need to build. If the design's wrong, incomplete, or late, it directly impacts every single domain of the project. That's why, to be effective construction project managers, we need to manage the design as effectively as we manage the budget, the schedule, and safety. It's not something we just outsource to architects or engineers and let them forget. It's something we manage as closely as any other phase of the project. So to understand why design management matters, let's move on to talking about what is design management. I want to give you a really clear definition and understanding of what it is, the phase it's involved, and the core concepts you need to understand. So what is design management? Well, before we get into this question, we need to answer another question. What is the design? Well, when we think of designs, we think of drawings, specifications, maybe 3D models, but what it really is, it's a set of instructions that tell us what to build, a set of instructions that capture the project requirements. Core to this understanding of what is a design is understanding what requirements are. Now, requirements are basically our clients or our principal's requirement for what they want us to build. Say, for example, we're engaged to build a new road. At the end of the day, what does our client want? They want a 4-lane highway, they want street lighting, they want drainage to suit a 1 in 100-year flood level, they want an asphalt surface. These are the project requirements. They're the principle defining what they want to build. Okay, so the next concept we need to understand is we need to understand the design process. How do we turn these requirements into a set of drawings and specifications, a set of instructions for what we need to build? That is effectively what the design process is. The design process takes certain requirements. So this might be a client brief. There might be functional requirements. For example, a solar farm, the requirements might be to export a certain amount of energy. And there might be compliance requirements. For example, there'll be certain electrical laws about how cables need to be installed, the insulation on cables, these sorts of things. Putting these all together, we get the project requirements. Then the design process, what it does is it takes these requirements and transfers them into a set of engineering drawings. Okay, so the next thing we need to understand is, what does the design matter? And we've already spoken about this a little bit, but the design is really what drives everything on the project. It's the glue that holds the whole project back. If we're building a 3-bedroom house versus a 4-bedroom house, the cost is going to be different. The quality standards are going to be different. The rules and regulations, the contract we sign will be different. The time it takes to build the project will be different. The safety requirements will be different. The people managing the work, the people we need to engage will be different. So really, what we build, the design, really drives everything on the project. Okay, so we understand the requirements, we understand the design process, we understand what the design is and why it matters. Let's now talk about what is design management. Well, the design management is the process of managing the design to ensure it meets the project objectives and fulfill the requirements. So it's ensuring the design that we develop, instructions of what to build, fulfill the project requirements, are constructible, can be built within our budget, on time, safely, and can be handed over at the end of the job. Really, it's about ensuring the design we develop and how we implement it fulfills every single one of these project objectives. So it's about taking the design, not looking at it in isolation, but looking at it in terms of cost, quality, commercial, schedule, safety, stakeholders, all these different aspects. It's about managing the design to achieve the project objectives. So to understand why the design matters and what is design management, we've given it a definition that it's about managing the design process to ensure that all of the project objectives are met. We're thinking about safety, cost, quality, schedule, contracts, everything. Now let's talk about in more detail the stages of design management. What are the stages of the process and what's involved in each of them? So there's 2 essential stages of design management. There's the design development stage where we create the drawings and specifications, and then there's construction phase design management. So design development takes the drawings from the initial concept, the requirements, to the set of issue for construction drawings. Construction phase design management is how we then implement the design. So if we think about this, the first stage, we're creating the drawings. The second stage, we're putting them into practice. So we're dealing with things like construction changes, capturing as-builds, dealing with new stakeholder requirements, managing new changes on new design developments. Okay, so I'm first going to go through each of these 2 stages in a bit more detail. So the first one I want to talk about is design development. So design development, we can break down into a further 2 stages. We've got the original concept design, which is we develop a broad outline of the project scope. We understand generally what we want to build. Then we've got detailed design. Detailed design is where we define exactly what we need to build to the minute details so we can give them to someone building it and they can go and build it. We can break these stages down a little bit more, where we've got the initial requirements analysis where the client determines what they actually want to build in the first place. So someone building a solar farm, they need to understand where the grid connection is going to be, how much energy they want to export, what's the most cost effective and feasible. They then develop a concept design, which is a broad outline of the project that shows roughly what they want to build, the layouts, the general technical requirements. Then goes into the detailed design phase where we develop the detailed specifications and drawings, which take it to issue for construction, which is when we can hand over the drawings to the construction team. And then finally the as-built stage, where we hand over the as-built drawings, capturing all the changes made during construction. Typically design development, we'd say, ends with issue for construction, but it's important to note that most projects will also do an as-built stage of the design where they create a new revision of the drawing, capturing any construction changes. Okay, so development is really about transforming project requirements into instructions as to what we build. That's what it's really about. It's about taking these initial set of requirements and turning them into detailed instructions we can give to someone building it, and they know exactly what to do. And essentially, the role of design development in this process is about ensuring that we get a design at the end of the day that fulfills requirements, it's approved by all of the stakeholders, everyone's signed off on it, everyone's happy with it, it's cost effective to build, it's possible to build, so it's actually technically feasible to build. Quite often you'll get design drawings that, for whatever reason, are just almost impossible to build or incredibly expensive to do so, and that we can build it on time and safely. Okay, so if we then talk about the core responsibilities in design management, what is the design manager actually doing within this process of design development? So what is the design manager doing in this process of taking the initial project requirements and turning them into an IFC design? Importantly, the design manager isn't the one actually doing the design. What are they doing? They're coordinating project requirements, so they're working with clients, authorities, and internal teams to understand and document the functional, technical, and statutory requirements. They're managing consultants, so they're issuing the scope of works, managing timelines, and ensuring all the design disciplines are aligned, so the civil, structural, MEP. The design manager will manage the consultants similar to how a project engineer or a project manager will manage a subcontractor. The consultant is the subcontractor to the design manager. They need to maintain the design program, so they need to ensure the design is developed on time, and it goes through specific design gates, which I'll talk about a little bit more in a second, but basically they're tracking and controlling the design schedule, ensuring the design is delivered in defined phases, and that the IFC date meets the IFC date in the program, so it's ready to start construction. On top of that, the design manager is coordinating all of the stakeholder approvals, so they're facilitating the design reviews with the client, end users, councils, utilities, whoever has to sign off the design so it's approved for construction. They're managing the review and coordinating the feedback. So what happens in these design gates is the client, stakeholders will make comments on the design, things they don't like, things they want changed. All these comments need to be closed out before it reaches IFC, and the design manager needs to manage this. On top of this, they're actually facilitating these design reviews. So they're organizing and leading the internal reviews for constructability, cost alignment, and safety and design. They're also ensuring budget alignment, so they're engaging with cost planners or estimators to check that the design is possible to build for the budget we've allowed for. They're also going to run value engineering sessions, so this is where they bring in the construction team, get them to review the design and look at cost-effective, cheaper alternatives. They're also controlling the design deliverables. They're maintaining the drawing register, they're monitoring the completeness and quality of the submission. So let's now move on to the other phase, which is once the design reaches IFC, what happens during the construction phase? What's the role of the design manager during the construction phase of the project? As you can imagine, things change during construction. There's issues with the design, there's value engineering opportunities, all these things change, and the design manager is essentially there to control the change and ensure the design aligns with the project requirements. Design manager during construction, it's moving from creating the design to controlling it. They are responsible for the design handover and document control, so ensuring there's RFIs and change management. They're also responsible for managing vendor design and shop drawings. It's a very important part of design management. They're managing the interface between quality and design as well. They're documenting any changes, or they're working with the construction team to capture all the changes and develop the as-built drawing set. They're also preparing the handover documentation. Typically, the design manager is also the one preparing the O&M manual, certifications, warranties, compliance documentation, getting it all together to submit at the end of the job. So what are the responsibilities of the design manager during the construction phase? Well, they're going to be the one managing the RFI process. They're going to be coordinating closely with the construction teams to respond to technical queries from site teams to consultants, ensuring these responses are prepared quickly, on time, they're correct. They're also the one tracking the RFIs and making sure they get closed out. They're also reviewing shop drawings, or at least sending them to the consultants to review. They're ensuring that subcontractor shop drawings comply with the design intent and interface correctly, and coordinating any consultant reviews. They're the ones controlling design changes, so they're evaluating the proposed changes to ensure alignment with the contract requirements, track approvals, and updating the drawings accordingly. They're maintaining the design registers and document control, so they'll update the drawing registers with any new drawings, RFIs. They'll control the NCR log, control versioning and all the approvals. They're managing design deliverables, so for instance the operations and maintenance manuals, test certificates and warranties. At the end of the day, they're there to support the design team, but also to control the design and again ensure that what we're building meets all of the requirements of the project. Don't worry if this felt fast. I'm going to go through all of these responsibilities for both design development and construction phase design management shortly. So the design contents. Designs are really broken down into a couple of different types of documents. We've got drawings, specifications, schedules, reports, and digital models. Okay, so to begin with, drawings. Drawings contain detailed product information, and they're traditionally what we think of when we think of design drawings. You can have different types of drawings, and we're going to do a bit more of a discussion on this later when we talk about how to read engineering drawings, but typically the types of drawings we'll have title pages, general notes, layout or plan views, section views, and if we're dealing with services or mech-elec and plumbing, we'll have schematics and symbol type drawings. Okay, next we've got specifications. So specifications supplement design drawings and design packages. They talk about things like quality assurance standards, construction methodologies, or certain tolerances we need to meet. For example, we might have a set of structural engineering drawings that show us the concrete work we have to do. We might have a concrete work specification that talks about what type of testing we need to do. They'll be captured in the specifications. The next type of design document we have are schedules. So schedules typically provide detailed product information and typically relate to materials. For example, we might, in a landscaping design package, we might have a plant schedule. On a building project, we might have a paint schedule with all the different types of paints we need to use. So the drawings, the layout drawings will show us which walls get what paint. They'll usually have a reference code like P1, P2, P3, P4. Then the paint schedule will tell us what the actual paint product is. So here, for example, it speaks about the color, the code, the wash, blah, blah, blah. The next type of design document we have is the design report. So every design package will have a design report associated with it. Design report details how the design was developed. It talks about the design rationale, the basis of design, how the project requirements have been met. In some instances, it'll actually list out the project requirements and talk about in detail that every single one has been met. That's referred to as systems engineering, which we're going to talk about later. It talks about the key decisions, why they made certain design decisions, maybe some cost assessments, also how the stakeholders were engaged and evidence of the stakeholder approval. So every meeting we have with our stakeholders, their comments, how we've closed out their comments, that'll all be recorded in the design report. And the safety in design process. So the safety in design process is how we go through and check that the design is safe to build, how the construction team check it, how the maintenance team check it's safe to be maintained. Evidence of how the safety in design has been done will also be captured in the design report. And the last and my favorite component of the design, if you're lucky enough to have it, makes building anything 1,000 times easier, are 3D models. I've done a couple of building projects and honestly don't understand how people did complicated buildings in the past without a 3D model. They make your life 1,000 times easier. So these are basically 3D representations of the drawings that show all the different design packages coordinated together. So in a typical design structure, for this building, you might have a civil design that covers the earthworks and bulk earthworks and maybe the piling. Then you'll have a structural design that covers the foundations, the structural steelwork, the concrete structure. You'll have an architectural design that shows all the cladding. You'll have a services design that shows the cable tray, the piping, and the plumbing. 3D models tie all this together. So in a single model of the building, we can see everything at once. And it makes your life as a project engineer or project manager 1,000 times easier because you're not going from section view to look at a drawing to see where the penetration is. You can just see it all in the model. They're unbelievably easy. You can also do some fancy things with them, such as clash detection. So during design development, 3D models are used a lot to check that services don't clash with structural steel, that architectural facades don't clash with services, all these things, and increasingly you're seeing people use them to actually develop the construction sequence within the design. Reading engineering drawings is an essential skill for anybody who works in the construction industry, from project engineers to contract administrators. In this video, I'm going to show you exactly how to do it. We'll go through the different types of engineering drawings, the different layout views, different section views, how to pull it all together, and how to understand what we're building from a set of drawings. Okay, so first up, what are the different types of drawings we need to understand? Well, there's layout or plan views, section views, schematics or symbols if we're dealing with mech, elect, and plumbing drawings, general notes which apply to all design packages, and I want to finish off with talking about some other things to consider when you're looking at drawings. Okay, first up, we've got plan view and top-down drawing. So a plan view is an aerial view of the project. It's imagine we're above the project looking down. What do we want to pay attention to when we're looking at a plan view? Well, the first thing we have are grid lines. So grid lines are references that are used throughout the set of drawings. So this grid line will be used in elevation views. So elevation views we're looking face on, and section views where we have specific cuts of something and we want to look at it in more detail. These same grid lines can be used. So that's useful when we're referencing, we're going from different types of drawings. We want to understand where we're looking at in the building or the project. We've got dimensions, so things such as the overall width of the building, or offsets. There's none shown on this drawing. Want to pay attention to the RL. So the RL is the level. You can imagine the height. Typically, it's a measurement in meters, which references meters above sea level. For example, you can have a slab level RL, you can have a finished floor level RL. If you've got a building, you might have multiple plan views with different RLs, or you can have a natural service level. So this is plan view taken at finished floor level of the building, which is at RL 31.25. You can have section marks, so you'll have a cut of the building. There'll be a drawing reference on the section mark. We can go look at that section if we want a more detailed view of what we're looking at. There'll be notes and tags, which talk about things like callouts for finishes, penetrations or structural elements, and we'll also have a north point that gives us an orientation of where we're looking. Okay, next up, we've got section views, which are cut-throughs of the drawings, which give us more detail. For example, this is a section view of footing detail F6. So in our footing schedule, we can see F6 is a type of footing. This is the section view of footing F6. So if you imagine the plan view, we're looking down, there's a whole lot of footings for the warehouse. In the section view, there's a detailed cross-section that shows us the exact dimensions of that. On top of that, you can see the grid line reference WB, WC. We can reference exactly where this is. The reason it's WB and WC is because that footing F6 is used in different grid lines. So what do we want to look at when we're looking at section view? We want to pay attention to where the grid line's inserted or intersected, so we can see where the section is cut through, exactly where that is. You can see things like the exact slab thickness. You can see structural elements. For example, this is showing the floor slab, the footing below it, the slab block out where the structural steel goes in. In certain architectural drawings, you'll be able to see things like structural elements, structural steel, how it ties into architectural claddings. You'll be able to see ceiling heights, clearances. On civil drawings, you'll be able to see things like subgrade layouts, blinding, waterproofing, and you'll be able to see other things like finishing and build up. So section views, depending on whether you're looking at structural, architectural, civil, mechanical, electrical, whatever you're looking at, will show different things. But basically, they're just cut-throughs of the drawings that provide us more specific information about what we're building. Okay, next up, we've got elevation views or side views. Plan view gives us top-down. Section views give us detailed sections of specific elements of what we're building. Elevation view is a side view of the project. So for example, for this warehouse, we can see the actual structural steel frame of the warehouse looking at it side on. What do elevation views typically show? Well, they'll show heights and RLs. So we know from the plan view that the slab level was at 31.25. There might be a different type of drawing that shows what RLs these heights are at. You can see better on plan views, things like openings, windows, doors, louvres. You can see finishes, so it'll show material callouts, maybe certain type of painting on the wall. You can see grid, again, these grid lines are showing up. WC is where this portal frame is. Again, that same grid line that you can see in the plan view and actually in the same section view. And you can see, it really, again, depends on the type of drawing you're looking at, but it'll show you all sorts of different things that you can only see from a side view. Okay, next up we have general notes. So general notes aren't drawings, they're just notes that you need to read in conjunction with the drawing. So for example, if you've got this building that shows concrete foundations, there wouldn't be a note on every single drawing saying 32 MPa drawing that needs to get approved by the civil engineer with a specific mixed design requirement. No, that'll be captured in the general notes of the drawings. We'll talk about the cover on reinforcement. It's basically to prevent recycling information on every single drawing. So general notes are global notes that apply to the entire drawing set. They're often missed but contain critical information such as project-wide assumptions, specification references, responsibility clarifications, design scope boundaries, these sorts of things. What I find happens a ton of projects, which is really frustrating, is the general notes always tend to contradict the contract or the scope of works. That's why you just have to you have to pay attention to what all these different documents are telling you. Okay, the next set of drawings we have a mech, elec, and plumbing schematic drawing. So this is where instead of seeing something physically how it's built, like the plan, elevation, section views, you could see that it represented the structure we were actually building. Schematic and MEP drawings typically use symbols to represent different components. So for example, you might have a single line diagram, which is a visual representation of how the electrical system is put together. So for example, this single line diagram is represented in a logical flow. It goes from the power source, the transformer, the switchboard, to the sub-circuits. All these different elements aren't represented by how they physically look, they're represented by symbols. So you need to have reference to the symbols, the abbreviations, to understand what they all represent. When you're looking at schematic and MEP drawings, there'll always be tag references. For example, this is transformer 1, this is transformer 2, this is transformer 3. They'll talk about control strategies, there'll be sizing and load data. The other type of MEP drawing you'll get, so you'll have some sort of, for example, electrical, you have an electrical single line diagram which shows the logical flow. You'll also have layout drawings. So the single line diagram is a representation of the overall system. The layout diagram doesn't show how everything's wired together, but it shows where everything is. So this really simple electrical layout diagram, you can see where all the wall lights are, where there's an exhaust fan, these sorts of things. So these are representations of where everything is in practice in the building. Typically, there'll also be a note against it which has an elevation height above it. So for example, this light is to be mounted at 2 meters above ground level. Okay, so what are some general tips for how you should tackle engineering drawings? Well, first thing I always tell people is don't just blindly look at drawings. Have a specific reason to be looking at drawings. It makes it 100 times easier if you're trying to solve a problem by looking at the drawings. If you just take out the drawings, trying to understand scope gets a bit challenging. So the first thing I want to do is I'll want to understand what the drawings are showing so I can prepare a list of RFIs to create the client. So my goal is to review the drawings to create a list of RFIs. Or if I'm doing an estimate, my goal is to review the drawings to understand the quantities I need to measure so I can do a quantity takeoff, or to build a schedule, or to develop a construction sequence. The order, I'll then look at the documentation. Now this is really important because you don't want to just dive into looking at a section view because you'll confuse yourself. Is if there's a 3D model, always look at the 3D model first. 3D models make complicated structures a trillion times easier than just flicking through drawings, trying to match up layout views with elevation views, with section views. Always start with the 3D model. You can spend 2 minutes looking at it and probably get a really good understanding of what you're building. Then I'll always look in this order typically: structural drawings, which show the key structures, the civil drawings, and then the services drawings. Typically, you want to first look at the plan view or the overview view if you've got ones, then the plan view from the bottom up, and then the elevation views. And look, it really depends on the type of project and what you're trying to understand. And there's a lot of different ways to do it. I find it 100 times easier if I've got a specific reason for looking at the drawings. So now we've mastered the all-important skill of how to read engineering drawings, let's talk about the 2 stages of design management. We're first going to talk about design development, developing the drawings and specifications, the instructions of what we build. Then we're going to move on to talking about construction phase design management. So the question we want to answer is, how do we best develop the drawings and specifications, the instructions of what we build that meet the client stakeholder expectations, but also align with our budget, schedule, safety, and quality requirements? Because remember, that's the goal of design management, to develop Instructions are what we build in accordance with the project requirements. So what we're going to cover is we'll cover through design development, the core concepts, the design development process, and then the tools and techniques that are used to complete it successfully. But first, to shape our entire framework of how we think about the design development process, let's talk about how can design development go wrong. So the first thing is that the drawings we develop don't meet the client requirements. So we develop a set of drawings, but they miss important electrical requirements, certification of occupancy requirements, and then we can't hand over the project. There could be errors or ambiguities that cause delays to the construction. Say we're about to start construction of a concrete slab, the surveyor goes to set it out, and then we realize the levels are all wrong, and we suddenly lose 2 weeks going back to the design team to get the RFI clarified. So we could have originally budgeted to build something. Through the design process, we get scope growth, referred to as gold plating, and we end up with something that we can't build for our budget. Say we set out to build a 3-story townhouse and we end up building a skyscraper. There's obviously not going to be enough money in our budget or time in our schedule. We could propose a design that is technically unfeasible, so it's not actually possible to build, and we could have delays to our design that delay our overall construction program. So that's how design development can go wrong. When we talk about the process and the tools and techniques, it's to address avoiding these issues. Okay, so next up, I want to talk through a case study of where this happened, my own personal experience of where these design development issues have come up. So we were installing a series of new utilities under a rail line. The original proposed bore, so horizontal directional drilling, if you're familiar with it, where you install conduits or underground services without open cut excavation, so drilling under track, was impossible. The angle was too steep, it was too close to rail, so we couldn't actually get the proposed methodology approved by our client, and then it was physically impossible to actually construct. We had to relocate the bore back, which meant installing new bore pits that clashed with new utilities, that clashed with other structures that were proposed to be built. It ended up costing us 3 times our original budget, and it delayed the project significantly. The impact is it was poorly coordinated, it wasn't constructible, and there were cheaper alternatives available that if we'd originally identified during the design stage, we would have avoided this. This whole process of design development I'm going to talk about is how you avoid situations like this. Okay, so next up, I'm going to talk about the core concepts of design development. We've got requirements, the technical solution, progressive elaboration, and design gates and reviews. These are the core concepts you need to understand design development. Okay, so first up, we've got requirements, and we've already spoken about this a little bit, but the entire design development process needs to begin by understanding the project's needs and objectives. These are what we're contractually obligated to deliver. These might be through a client brief, stakeholder input, stakeholder specifications, or an early stage concept design. If I give you an example for a solar farm, requirements might look something like capacity. We need to build a 50 megawatt solar farm. There's certain grid connection requirements. For example, we might need a harmonic filter in our substation to deal with poor power quality. There might be environmental requirements. We might have to manage drainage and runoff from the access tracks during heavy rainfall. There might be community requirements. Our community might want us to have, they might not like the look of the solar panels. They might not want to be able to see them from the highway, so we need to install a landscape screen. And there might be maintenance requirements from the operations and maintenance team. They need to get in there and cut the grass, so then it might need to be a certain width between the rows of panels so that we can get a slasher in there. So these are all examples of requirements, things the project needs to deliver to be successful. Okay, the next important concept to understand about design development is the technical solution. So the technical solution is the coordinated set of drawings and specifications that meet these requirements. It's our solution to the problem the requirements present. How do we develop something? How do we develop something to build that fulfills all of these requirements? So for example, on our solar farm, we might choose our high voltage equipment to meet the certain grid connection requirements. We need to then choose our drainage design to ensure water runoff complies with the environmental protection requirements. Then we need to develop a panel layout that's optimized for maintenance access. So we're making technical decisions to develop a technical solution that needs to fit all the requirements of the project. Now, the next super important concept to understand about design development is the idea of progressive elaboration. The design develops progressively. What I mean by this is that we start with a high-level concept, our requirements, and we add increasing levels of detail throughout time. So for example, for our solar farm, we know it has to meet 50 megawatts. We might start with a broad layout of where the panels and the inverters are going to show that we can fit all the panels on the land allocated to the project. We then choose the inverter and the DC cabling to confirm where all the different blocks are going to be, how all the panels are going to connect to the inverters. We choose the layouts where the inverters are going to go. Then we start to move things around a little bit to optimize and reduce the amount of underground trenching and cable install we need to do. And once we've got these layouts, we can optimize our drainage design to reduce the amount of subsurface drainage and to ensure we meet the environmental requirements. And then by the time we get to an issue for construction drawing set, we've got every trench, a set out location, a depth, an orientation. We know where every single pile is going to be. We know every clearance shown on the layouts, and we know exactly where everything's going. But we don't start with just the solar farm and then start by orientating where all the piles are going to go. We go through a process of progressive elaboration. Now, what tends to happen is that we break down this process of elaboration into formal stages referred to as design gates. So the design is reviewed in stages, or developed and reviewed in stages, with these formal review points where it's issued to stakeholders, the client, other key people for them to review. And it's this way of checking that the technical solution is developing and progressing on track. So it's avoiding all this wasted design effort, going from developing an IFC design with every single pile layout and then realizing that the drainage design doesn't work, so we actually have to move everything a slight bit, creating a whole lot of design rework. So the purpose is we have set stages where the design's developed, a bit more details added, it goes out for review. A bit more details added, it goes out to review. So the typical stages that we refer to as design gates will be the tender or concept design, which would be a 15% design, the preliminary design, which might be a 30% design, the detailed design, 70% design, the final design, which is all the detail in the design, but there just hasn't been a final review, we refer to as a 95% design, and then the issue for construction or approved design is the 100% design. This is the set of drawings that we're ready to build off. Okay, so at each of these design gates, there's a review of the client requirements to ensure that what we've designed so far, up to 15%, up to 30%, does comply with the client requirements. There'll be a cost and constructability review, so we review that what we're proposing to design still aligns with our budget. There'll be some sort of safety and design assessment to ensure that what we're building is going to be safe to build, maintain, and operate. There'll be comments raised from stakeholders. They'll question certain decisions, they'll question compliance, or they won't like things about the design and want them changed. Then these set of comments need to be closed out as we progress through the design. Okay, so that's the core concepts of design development. Let's now talk about the tools and techniques we use to actually develop the design. So what tools do we have available to ensure the design complies with the requirements of the project and it's cheap and easy to build? Okay, so the first one is stakeholder reviews. So this is where we, at each design gate, the drawings get sent to our stakeholders for them to review and approve, and they'll be able to raise comments on the design, things they don't like, things they want changed. Again, the purpose of this is at each design stage, we're picking up compliance issues of things our client isn't happy about. Again, if it progresses to IFC and then they want something changed, it creates a whole lot of design rework and will delay the design getting to IFC, which is going to push back construction. So what's an example of the type of comments? So you can see that this is at a 30% design that this reviewer, AB, has made a comment about AS 4100 and they want the handrail heights to have been checked to ensure they comply against disability standards. There might be another example of a comment from JH where maybe the maintenance person and they want all service enclosures in the roof to be accessible by a scissor lift. So they're thinking about it from the maintenance requirements. They'll raise this comment, and then as part of closing out the next revision of the design, so these have been raised at the 30% design, at the 75% design, the designers will need to confirm compliance against each of these standards. So for example, they've just responded to say handrail heights are all 900 millimeters above finished floor level, which complies to AS 4100. So rather than changing anything in the design, they're just saying, yes, the design does comply and providing evidence of it. Design comments can be closed out a couple of different ways. You can If it is a non-compliance, you could update the design to comply. You could provide evidence like they have here that the current design does already comply, or you could prove that the requirement does not apply. And the final option, which would be a variation of the contract, would be to actually change the original requirements if the reviewer is insistent that they want that requirement. Okay, so who is actually making these comments? Well, really they'll come from two broad groups. They'll be from the client, the one paying for the project to get built, or from external stakeholders. So for the client, it might be the project team, the operations and maintenance team, technical reviewers, or the construction verifier, so an independent third party that the client is paying to check compliance with the drawings. Comments can also come from external stakeholders that are impacted by the project. You might have a utility that's impacted. Say a utility is getting relocated as part of the project work. That utility will want to review the design that shows the utility relocation and where the new utility is getting installed so they can ensure it complies with their services. You might have council reviewing the design, road authorities, government agencies, or people who have to authorize permits like certificate of occupancy permits to check compliance. Okay, so the next tool we have available, which is more suited to large projects, is systems engineering and formal compliance management. So this is where every requirement in the project requirements, so you might have the project specification, you might have other specifications that apply to the project, is documented and there's evidence that the design complies. This is a systematic way of going through all of the project requirements and verifying that every single requirement has been met and the technical solution meets all of the project requirements. So for example, this requirement to provide using our solar farm example, this requirement to provide 50 megawatts of AC capacity is in the project brief. There's evidence that it complies. The system is sized to deliver 50 megawatts at point of connection, and the evidence or reference to that is the electrical layout drawing EL001 compliant. So another example, RQ002, the second requirement is to meet grid connection specs, including the harmonic limits. The source of this is the grid connection study. So the grid connection study would be a source project requirement that the developer might have produced. And the design response is the harmonic filters included in the design. The inverter specifications match the utility limits. And they've shown that with the single line diagram, and then it's shown to be compliant. So this is just a systematic way of identifying every single requirement in the project, checking it complies so nothing's missed. Okay. So far we've spoken about managing compliance and approval from stakeholders. What about in terms of the other benefits of design management, which is about optimizing costs, schedule, constructability? That broad set of tools and techniques come down to bridging the design and construction gap. I don't know if you've worked on projects where there's been a poor design, but sometimes it feels like the person who's developed it hasn't paid any attention to how it's going to be built, how much it's going to cost. They've just quickly put something together and then you're expected to build it. So the most effective way we can avoid this happening is by bridging the gaps between the design and the construction team. The challenge you have is that designers tend to not spend much time on site. They don't really tend to build things. On the other hand, builders don't see what goes on in the design process. They don't understand the specific challenges, constraints, maybe there's time challenges, requirements that they're not aware of that they have to be met. The effective solution to all the other tools and techniques we talk about are just about bridging the gap between the design and construction teams. So the construction team have a better idea of the design constraints and the design team have a better idea of the construction constraints. The strategies we can use to do this is early engagement of the construction teams in the design process, constructability and cost reviews through design gate. So I said that that's a typical part of the process. It is and it isn't. You often don't see it done properly, but if you have at each of the design gates, you have a fixed constructability review, you re-estimate the construction cost, you get the construction team to review the drawings and advise if it's feasible to build. And effectively, if you get the construction team early, what you find happens is you get a shared ownership of the design output. If the construction team are the one reviewing it at each design gate, they're the ones saying, yes, this is feasible to build. They're signing something to say they've built it. They're not going to be as quick to blame the designers during the construction phase because they are the ones who've put their name to it as well. And so what you achieve by bridging this design and construction gap is that you identify value engineering opportunities early. So value engineering opportunities are basically the process of finding smarter, cheaper, more effective solutions, more effective technical solutions that still meet the project requirements. We can't change the project requirements unless we're the client. They're set, they're what we've signed up to deliver contractually, but what we can change is the technical solutions, so how we propose to deliver them. And again, this comes from bridging the design and construction gap, because often it's the construction teams that come up with some of the best solutions to the design problems. The key principles behind this is collaboration, the two teams working together, and then this idea of divergent thinking. So things like university teach you that there's one solution to a problem. You're pumping out a calculation. In the real world, on construction projects, you need to develop the skill of divergent thinking. This is where you're not coming up with one solution to a problem, you're coming up with 20 solutions to a problem and understanding what the best solution to that problem is. For example, say we're doing a tunnel project and we need to install emergency lighting. There's 100 different ways we could achieve this requirement. You could have battery integrated lights. You could have a central uninterruptible power supply and run an essential supply to each of the lights. You could have diesel generators instead of a battery backup. You could have redundant power feeds that achieve that same level of reliability. And effectively what you want to do is you want to come up with as many solutions to the problem as you can and choose the best one based on cost, simplicity, and compliance. At the end of the day, there's 100 solutions to any problem. This doesn't just apply in design development. This applies at all phases of the construction project. There's so many decisions we make. The real skill isn't necessarily in always choosing the best decision first. It's about understanding how to come up with a lot of solutions to the problem and identify the best possible solution. Okay, so just to quickly recap what we've spoken about. There's a staged process we follow through design development where we progressively add information. We go from early stage concept design through a detailed design process and finally to an issue for construction drawing set. The benefit of this is that we lock in major decisions early, everyone agrees to them, and then we add detail later in the design process, which saves design effort but also ensures there's not delays to getting the drawings approved, and the drawings that are approved everyone's happy with. It's one of the best techniques we can use to do this is to engage the construction and cost teams early and get them involved in the design process. We can track compliance and project objectives continuously, and we should always be focusing on value engineering, coming up with the best solution to the project requirements. As we know, the role of the design manager doesn't end when the drawings get an IFC stamp. Design managers play a huge role during the construction phase. Next, we're going to talk about construction phase design management and how to successfully ensure the technical solutions implemented and we comply with the project requirements. So construction phase design management, also referred to as CPS, is basically everything the design manager does after the drawings get an IFC stamp. So these include procurement and vendor design coordination, often referred to as submittals, change management and managing RFIs, so what we do when we need to change the drawings during construction, temporary works design coordination, so any non-permanent construction works like false work or access tracks we need to do to implement the technical solution, and then also any design input required for completions and closeout of the project. Okay, so first up, talking about procurement and vendor design. So even at the issue for construction stage, design is really not fully complete. Often the vendors we choose will develop shop drawings and specifications that must comply with the project requirements. As an example, say the initial design just shows a single line diagram of a switchboard with basic power ratings and size requirements. The switchboard manufacturer will develop a set of manufacturing drawings that show exactly what they're going to build. These are referred to as shop drawings or fabrication drawings. This set of drawings will also need to be approved and checked by the design team or the design manager, depending on their capabilities. The design manager needs to coordinate this review to ensure the drawings comply. And quite often when you get to the vendor design stage, you'll actually start to identify some issues with the core design. So it's an incredibly important stage, and it very much applies to material suppliers. So paint specifications, maybe the types of plant we're using for landscaping, the types of facade we want to use on a building. Typically on building projects, there's a significant amount of vendor design, and all this needs to be done and coordinated before materials are ordered. So the approvals of vendor design can have a huge impact on the overall schedule of a project. Okay, So the next core role of the design manager during the construction phase is change management and RFIs, requests for information. So changes during construction are inevitable. There will not be a project without an RFI. Common drivers of these would be things like design errors and omissions. Maybe there's missing detail on a drawing, or maybe the set out height of a slab is wrong. Constructability issues, so things might not be physically possible to build. Site conditions may be different to expected. For example, maybe there's a lot of rock in the ground and we want to raise an RFI to do a shallower trench. There might be value engineering opportunities that picked up, cheaper, smarter ways to do things that we want to request to implement. And in some instances, maybe a vendor might not be available and we want to substitute another vendor. So these changes will occur on a project. The goal of effective design management is to minimize them or identify them as early as possible. But the reality is any project you work on, there will be RFIs that need to be raised. Okay, so what's the RFI process? Well, the construction team will come across an issue or want to propose a change. They'll complete an RFI or request for information submission form which details the change they want to make, information, what requirement it refers back to, and potentially their proposed technical solution if they've already got one. The design team then prepares a response for this, so the design manager needs to coordinate sending it to the design team, reviewing it, and issuing a response to the construction team. The construction team, if the RFI is approved, they'll then implement this change and capture it in the red line markup drawing set to close the RFI. So they implement the change, so they've shifted a trench a meter across. They'll then need to mark up this change on the drawings so that there's an as-built set of drawings developed showing what's actually installed. Okay, the next core role of the design manager during the construction phase is temporary works management. So to facilitate the construction, there'll need to be a whole lot of non-permanent structures built, such as false work, so supporting concrete slabs while they're poured, scaffolding, excavation or shoring if we're doing deep excavations, or crane platforms. These non-permanent works won't be captured in the original design as they're not part of the finished technical solution. They're non-permanent solutions developed during construction. The design manager will typically manage the temporary works design process, or if the project's big enough, there might be a separate temporary works manager. The design manager coordinates the independent engineering and review to ensure that it's safe, compliant, and suited to the task. Okay, the final core responsibility of the design manager is completions and closeouts. So this is really the final phase of the project where we're handing over all the documentation to show the client that we've built it correctly. The design manager usually plays a significant role in this process, and on a lot of projects I've worked on is the one actually tying this all together. So examples of the type of responsibilities would be developing the as-built drawings, compiling the markups from RFIs and site records, sending these to the drafters as long as any other inputs like survey data, so that the drafting or the engineering consultant can produce the final as-built drawing set. This is the set of drawings that the maintenance team will use to maintain the asset, that show where everything's installed, what was actually built at the end. They'll also assist with things like the preparations of the operations and maintenance manual, the certificate of occupancy. They might do some sort of owner training, or any completions inspections. The design manager usually plays a huge role in this process, and the goal is to show the owner that we've built something that complies with the original requirements and to help them facilitate their transition from the construction phase to the operations and maintenance phase. Some other responsibilities that the design manager might have would be maintaining a design changelog, so an RFI register that tracks all approved changes and their impact on the cost and schedule. They'll be heavily involved in document control, so the design manager is going to be liaising very closely with document controllers to ensure they've got the correct versions of the drawings on the system. Any RFI responses are documented so people aren't working off the incorrect revisions of drawings and specifications. They'll deal with interface management, so especially in multidisciplinary brownfield projects where there's a lot of different design interfaces, there's a lot of different stakeholders involved in the project. For example, in design development, they might be the one liaising with the utility about developing the plan for the utility relocations. During construction, they'll probably be heavily involved in getting the final sign-off and approvals for the utility that they're happy that their service has been relocated correctly. So they're very heavily involved in stakeholder management like that. Some designs might have specific design hold points that require approvals from the original engineering consultants. You see that a lot in pre-pour inspections and structural work, where the actual structural engineer needs to sign off the drawings or sign off the concrete before we pour concrete. The design manager will typically be involved in that approval, and that ties into the quality assurance process. So ensuring all the changes are made, documents are controlled in accordance with IS 9001 or specific project quality assurance standards. Okay, so just a brief recap. As we've established, the role of the design manager does not end at the IFC stage. All vendor and temporary works designs need to be approved. All design changes need to be formally reviewed and controlled and assessed and approved. The as-built drawings and operations manuals need to be produced, and the client, at the end of the day, wants to receive a final product that shows their original requirements have been met. So it's not just taking the design from the requirements of the IFC. They want to see that the requirements they've originally set out for the project have been met in the completion stage of the project, and the design manager plays a huge role in tying all of this together.